Dobro večer svima, još jednom. Prilika je dobra da ugostimo doktora Nebojšu Mojsilovića, koji je predavač na Institutu za konstrukcijsko inženjerstvo na ETH u Zurichu. I danas imamo jednu lepu temu koja je zapravo onako vrlo interesantna za oblast zidanih konstrukcija, što je za, ajde da kažem, tržište Srbije i našu domaću praksu onako retkost da imamo iz prve ruke šansu da čujemo. Doktor Mojsilović je dokazani ekspert iz ove oblasti, u čemu svedoči brojne nagrade koje je dobio, kao i njegove posete studijske raznim univerzitetima u svetu. Nebojša, ja vas molim da prezentujete svoj rad i nakon toga će uslediti diskusija. Ostale prisutne molim da utišaju mikrofone kako ne bi došlo do nekih zvučnih efekata, budući da se ovo sve snima. Izvolite.
Okay, hvala Vladimire. I will switch now to English. Thank you, Vladimir. I would like to present you some research that has been done at ETH in Zurich at our Institute of Structural Engineering on the enhancing in-plane performance of masonry walls through introducing soft layer membranes. First slide shows actually what are the goals and the mission statement of our Structural Masonry Group. Actually, since I'm retiring early next year, so I'm the only person now, only member of this group, but it will be, there will be another group after I leave ETH next year. So the goals for our group are the performing of high quality research, then to educate professional engineers, support national, international research and professional organizations in the area of structural masonry, satisfying highest demands regarding judgment and independency. And this is actually, in my eyes, the most important thing in today's science, where a lot of companies are coming with funding of research that is actually targeted to something that they can use. So I think these judgment independency are very, very important. And of course, after that, the idea is to transfer this knowledge to practitioners through structural co-development and presentations to the practitioners. So the major research projects that were done in this group are deformation capacity of structural masonry, then reliability of structural masonry, hybrid testing, advanced measurement techniques were developed, and the topic that I'm going to talk in detail about is the development of soft layer for seismic response modification of structural masonry. So the idea is to apply some modification approach to unreinforced masonry structures, typical for Switzerland. Well, if I can say there, about 85% of all masonry structures are unreinforced in Switzerland, because there is only one part in the west part of the country that could be earthquake prone, a little bit more than, let's say, very small extentations. So we developed a composite sliding layer. We call it multi-layer bed joint, which were introduced. This multi-layer bed joint is comprising of two elastic layers, which are 2.2 millimeters thick, and one rubber granulate layer that is put in between them. And then we did a lot of tests to determine the seismic performance of this layer and, of course, the whole structure. And we tried, of course, to develop some recommendations for the practical design. We did a lot of tests on large full-scale walls, on small walls, on the triplets, everything you can imagine. After this testing, which was actually financed by a Swiss National Science Foundation, we have got money. Professor Stojedinović and myself, we were co-investigators. We got money for 4 years, so we were able also to develop some mechanical models that can describe the behavior of this joint and the behavior of the wall with the joint. So now I will go in detail to to this testing. So I will speak about materials, about the program of testing, results, and some discussion, and of course conclusions. And all this can be found in these publications, publication that is put down in engineering structures in 2017. And actually the most of this work were done by Dr. Miloš Petrović, who is now working in one design company also in Switzerland. So the materials we use standard clay block. You can see here the picture that is typical for Switzerland. So we have about 45% of void area, and the clay blocks are again used maybe in 80% of all applications. Small part is used in calcium silicate blocks, and very small part is used is the concrete blocks, and they are actually used in this western part where the earthquake accelerations could be larger than in the other parts of Switzerland. Then we use standard cement mortar, and we always fill bed and head joints, and thickness is usually 10 millimeter. In contrast to other countries, also in Europe, in Switzerland, we use exclusively standard cement mortar, so there is no addition of weaker elements in it. So these typical soft layers that we use are looking from left to right: extruded elastomer, then rubber granulate, then cork, then cork rubber granulate, and bitumen. So we tested all of them in order to find out which one is actually the best for our purposes. And here you can see this multi-layer bed joint. It consists of this core soft layer, which is put in the middle of the joint. Then we have these two protective elastomer sheets, and then we have mortar. So this on this photo on the left side, you can see how that looks like in reality. And of course, this joint is then thicker than 10 millimeters. It's about 17 to 18 millimeters. This is our testing program. So first we did some preliminary tests, and the idea was to find out which core soft layer would perform the best for that what we need. So in the first 4 tests, we tested the walls with the layers of rubber granulate, cork rubber granulate, cork, and bitumen. And you can also see the layer thicknesses. They ranged from 2 to 3.5 millimeters, and the walls were, well, we call them small walls, 1.5 times 1.6 meters, and thickness was 150 millimeters. The aspect ratio of these walls was actually near 1, and we always put some pre-compression on these walls, and you can see here on the right side we have 10% of the masonry strength, masonry compression strength we put that on these walls. After discussing the results, we then decided to use the rubber granulate as core soft layer for the main series, which is then denoted by Z, and we did 5 tests. These walls were larger. So the typical wall was 2.7 meters long and 2.6 meters high, with aspect ratio 104. And then we did one wall which was very long, that is the ZX, 3.6 meters. And also we did one wall with 1.8 meters length. So in order to actually see what is the influence of the aspect ratio, and looking at pre-compression, we also did here 3 possible, we chose 3 different levels: 0.05, 0.1, and 0.2. That means 5, 10, and 20% of the masonry characteristic strength in X direction. X direction, that is actually vertical direction. So this slide is showing how we prepare these specimens. So this is what we already actually seen. What is interesting here is that having a hollow clay brick, we have the strength of the brick was 31.2 megapascal. The strength of cement mortar was 10.5 megapascal. And at the end, one gets actually the masonry compressive strength of 5.2. This is how this is actually done. First, you put a layer of mortar, then these 3 elastomer and coarse soft layer sheets, and then again mortar, and then the bricks. These are the 4 soft layers that we tested, which I already mentioned before. So this is our test setup. That is the typical 3 actuator setup. You can see on the right side the schematic drawing. We have the wall. On the wall there is a loading beam sitting, and we have 2 vertical actuators and reaction frame and 1 horizontal actuator. And at the beginning, of course, we first apply this pre-compression using the forces in vertical actuators. They have then the same force. After that, we introduce the horizontal movement actually through this horizontal actuator, and the wall was double fixed. That means that this loading beam in the middle, it was always horizontal, so it could move up and down, but it stays horizontal. And then, of course, that had actually, as a consequence, the change of the forces in vertical actuators. So they have to equilibrate this horizontal force times the height of the wall, this bending moment. So, as I said, first we pre-compress the walls, then we introduce this static cyclic shear load that was computer controlled displacements, and they had a sinusoidal wave form. We introduced every step 3 times. We simulated, as mentioned, actually fixed end boundary conditions, and use two-dimensional digital image correlation measurement system to obtain deformation of the formation field of the specimen. So this is this DIC measurement system that actually we developed in-house. So you have a camera, as you can see in this part here. On the left side, we have flashes, and we put some randomly distributed speckles on the wall surface, so that we can change, that can then follow the change of the formation. That means the position of these points on the photographs. You can also do the large wall with that, and also you can check here the movement between this bed joint and the bricks. So very fine measurements can be done with this system. So the results of preliminary phase, you can see here the walls that were denoted by WG, WGK, WK, WB, and P1 is actually the wall of the same size, same material, but without any soft layer. So we use results of that wall P1 just to make a comparison. And as it can be seen, the drift ratio, that is delta U, was measured, and delta U in percentage is actually the increase of this deformability. And you can see by rubber granulate, we can achieve almost 120%. That is one thing that is important. And the other thing is, of course, that the force that we achieved, that means this H max and H min of these walls with layers compared to the results of the wall without layers, P1, you can see that we have force actually drop. So this force would be smaller. So delta U is going up, and delta H is going down. These are the failure modes, and the typical X failure mode could be seen by the wall WK, that is cork, and this one also didn't show so much modification. And the other walls, when you can, for example, on the left, you can see that this failure is actually V-type. That means, let's say, a half of the X, and the similar situation was with WGK, that is, and WB, that is bitumen. So we decided to take these WG results, that means the rubber granulate, for the next phase. Before I forget, we also did in the framework of the other research project, we also did the same test on the same walls with the same material, but without soft layers. So we have a series of tests on the large walls, and they were denoted as a T, so we can compare them. But first go here. This is the hysteresis of wall WG, and this is the hysteresis of wall P1. So one can clearly see that we can dissipate much more energy, and that the failure is coming on the lower forces. Here we can see now the results of this DIC measurement. That is the major principal strain for the wall WG. That is the wall, small wall 1.5 times 1.6 meters. So on the left side you can see the formation of hysteresis. On the right side you can see the development of major principal strain. So the larger the strain, the more reddish would be the deformation on the right side. So this is actually not some finite element simulation, it's just the measurement that we did with the IC. And you also can see rocking. On the top, on the bottom of the wall, there is a multi-bed joint, multi-layer bed joint. And of course, eventually the wall will be destroyed through recycling. So these are now the results of the main phase. So as I mentioned before, we have here two series of walls. T1, for example, is the same wall as the Z1. Well, not the same wall, but the same dimension, same material, but without soft layer. And you can see for this first wall, we could achieve increase of 340% of story drift ratio. For wall Z2, we get almost 5 times larger displacement. Z3 was only 80%, Z5 50%, and Z6 120%. So in this case also, this is going up, and the force that can be achieved is going down. So that's the similar situation as before. And these are the failure modes. And as you can see here, there is the walls were destructed, except the wall Z2, which actually stayed as it was before the test. But in the other walls, we have actually the physical separation of the parts of the walls that can be also seen later. We will see that later. So this is the same thing as before. Major principal strain for wall Z1. This is now the larger wall, and again on the left side we have development of hysteresis, and on the right side we have development of deformation. So what is here interesting, that actually the unloading, you can see that on the left side, the unloading parts are actually speed dependent, which then allow for certain horizontal falls relaxations that are these small drops in diagram. And actually in the case of these sinusoidal loading that we had, this drop appears in the region of the peak displacement. That means when the speed, the loading speed is almost zero. And you can see on the right side that there is a wall, part of wall is separated, and now only the left side of the wall is working, and the right side is just staying on the side. And in spite of that, we see very similar cycling and hysteresis for cycling. Just at the end, it will be a bit different. So this is the wall Z2. This wall was actually had recompression load on only 5% of the strength. And on the left side, you see the wall T2, that is the wall without layers. And this is very nice hysteresis because the vertical load was small. So theoretically, you can apply here displacement, very large displacement, which of course in reality is not possible because you have some other walls that are connected with this one. But this is just to show how much energy actually this can be dissipated through the system. And when you check the failure modes on the left side, this is the wall without layer. We have here typical sliding failure. That means that the joint, the horizontal vertical joints are actually destroyed. On the right side, you can see the wall almost without any deformation. It was just sliding on this joint at the bottom of the wall. This is the last wall, Z6, and you see comparison between the Z6 and T6. Once more, that were the same dimensions of the walls. These were very long, through 3.6 meters and 2.6 meter high, and you see the difference in the hysteresis. And also on the right side, you have almost two different hysteresis, and that is connected with these failure modes. On the left side, you see, let's say, the typical failure of the wall without, this is without bed joints layer. And because the wall is long, you don't have any more X, you have just H failure. And on the right side, you see that the wall is actually divided in three different parts. And then you have this rotation of the hysteresis in the diagram. When we took the wall out of the setup, we could inspect these joints, and you can see them here. The middle one is the granulate, and upper and lower are actually extruded elastomer. And here that's given in detail. So actually in this case, we also had the elastomer layer that should protect the middle one also failed here in tension. So in discussion, I think this is actually a very interesting thing. When you connect the wall T6, that is without any layers, plus layers, you get wall Z6. And then instead of the system that we had, so double fix wall, and then we have this H-type failure. When you introduce these layers, you actually get, let's say, a half of the wall T6. So that means you have fixation on the top part, and on the middle part, you have actually the horizontal joint. And on this slide, you can see all the hysteresis of these different walls, starting with small walls, the first four diagrams, and then the next 5 are the larger walls. So the main point here is that we can dissipate much more energy introducing these layers. And actually the idea to do this project was that the people that are building in Switzerland, they are putting these layers as a sound insulation or waterproof layers, and they don't think of them like something that is going to modify the earthquake response. So we actually, that was the reason that we checked all that. And for example, if you check just the simple strengths, if you put these layers between the wall, you can get 10 to 15% loss in the strength. So nobody took care about that. So we decided to invest our time and to see what is actually happening with all that thing. And this came out, which is actually very good, especially for the Switzerland, where you don't have such large extentations through earthquakes. So in conclusion, we can reduce the initial stiffness for about 20 to 40%. Then we reduce the horizontal resistance, it's about 30%. And we increase the deformation capacity that goes up to 6 times higher. And we can increase, of course, the energy dissipation. So in general, this seismic performance is then improved in that we delay the significant strength and stiffness degradation. We enable sliding motion along the multi-layer joint. Once more, it is important that actually that cannot go, let's say, in infinity, but you have other parts of the building that would stop that. And the last but not least, you can enable the quasi-ductile behavior of structural masonry. So that was the part with the testing, and then we did some analytical modeling. So we tried to find some model how to predict the wall failure modes. That means to see where these vertical cracks are appearing because they eventually led to the wall separation. And we used the simple stress analysis and found out that can really work, which was not so actually to expect. We start for the typical stress distribution for linear elastic behavior, because we could have the moments on the top and the bottom of the wall. Then we have the linear distribution of the normal stresses, and we also assume that the shear stresses are parabolically distributed over the wall, which are the typical assumption that we use in linear elasticity. So we have here the governing equations, the stresses at the bottom, the normal and shear stress are given these equations, and when we integrate these stresses, we can get resistance force that is here denoted with R, which is of course the function of the position of the wall. Y is the axis that is going horizontally, and we have also demand force, which can be also calculated through integration over the length of the wall. So for demand force, we integrate the stresses, and for resistance, we use cohesion and the angle of the initial friction. When we calculate that, then we can predict where we could have these cracks. So on this diagram, that is the example for wall Z3, we take the movement from left to right. So this is the load, the shear load direction. And then at the point where we have the demand that is larger than resistance, we should get the crack. So this is given here for the wall Z3. So tensile stress location should be between blocks 2 and 3. That can be seen also from diagram. And for the compressive stress location, we get the positions, so between blocks number 7 and 8 and 8 and 9. So that is the prediction. And of course, we could check that using our DIC results. This is given here for walls Z2 and Z3. So for wall Z2, we predict that the tensile stress location would be between blocks 8 and 9, which is actually the case, as it can be clearly seen for a DIC measurement. And for wall Z3, the tensile stress location was between blocks 2 and 3, which is also correct. And compressive stress location for the wall Z3 was 7 to 8 or 8 to 9, and it was actually 7 to 8. And for wall Z2, it was between the blocks 1, 2, and 2 and 3, which is not actually here clearly seen, but it is almost at the block number 1. So this failure mode and displacement capacity of masonry walls with a multi-layer bed joint, they were governed by the extent of shear and tensile vertical cracks that developed from the bottom cores. And the initiation and propagation of the vertical cracks eventually led to this disintegration of the walls. That means the reduction of the effective shear transferring wall area. So we developed actually a model which is capable of predicting the position of these cracks, and that was validated through these experiments. And this is self-explanatory, but these days maybe it's always important also to say such things. So one of the recommendations from this study is that engineers must carefully consider the distribution of the shear stress along the bottom of the wall. Well, in my time when I was a student, nobody would say something like that, but now when I'm teaching other people, I know that I have to mention this, otherwise. So after this, we did some, let's say, more complicated or mechanically complicated models. First, we tried to develop an analytical model for the loading speed dependent in-plane horizontal force displacement behavior of the walls with multi-layer bed joint with the rubber granulate core. And we combined the rheological model for the joint and the linear elastic model for the masonry. And in that way, we could predict the behavior of the walls. So this is the typical rheological model. So viscoelastic model comparing of the spring, which is characterized by the shear modulus. Then we have on the upper part dashpot, which is characterized by this parameter zeta, which is loading speed sensitive viscosity parameter, and had a dimension of time. And on the lower part, we have the frictional slider, and this is characterized by tau y, that is the sliding resistance. I'm not going in detail here, but at the end, you get then the dependency of the shear force and slip. So H is the shear force, D is the slip, the dot is the slip rate, of course. This delta TML, that is actually the thickness contraction due to vertical forces. And we also here introduced this parameter psi, which is actually characterize the stiffness degradations through the cycling testing. The important thing is to actually see which part of deformation can be contributed to shear, flexure, shear of the joint, and to rocking. And for that, we need this long, that's not equation, but just definition of the elastic stiffness, KL. And we have these 4 parts. The first part where we have this kappa, which is actually the how do you call it correctly, the coefficient that is used for the cross section is 1.2 actually in this case. Then we have alpha. Alpha is the 0 moment position with respect to the bottom of the wall, and then that is used for the flexure part. Then for the shear of the multi-layer bed joint, we have the third one, and the last one is for the rocking. And you can see in the table, the largest contribution is actually here, as one can expect, due to the shear of multi-layer bed joint. So all these numbers in this table at the end should give 100%. I think that should be correct. So when we take care about the stiffness degradation, which is very important in here, you can see on the diagram how these parameter here is that now C1, which is dependent on the number of the cycles, and is here the number of the cycles. K0 is now the tangent stiffness, and that is actually 1.4 times the elastic stiffness that we had before. But now here we introduced also this stiffness degradation parameter. So it's getting a bit complicated, but you can all that can be, of course, calculated with the computer. So at the end, we can compare prediction with experiment. So first, the horizontal force resistant. This is the equation which is given here. That is the how we calculate the horizontal force is dependent of the this slip or D. And on the diagrams, you can see the comparison between calculated and measured force resistance. And of course, if it is ideal, then all these red points should be on the diagonal, but with masonry, there is no ideal thing. So we have some, but actually, I think that this is actually very good for the masonry. So I'm very satisfied with this model that we developed here. The other one is not so perfect. This is the model that we use to connect horizontal force with the horizontal displacement. And as you can see, we have parts of the elastic, that is the beginning. Then we use model viscoplastic, and this can be only used for loading path. For unloading, this model does not work. That is something that we didn't succeed to develop. But anyway, I think the prediction is not so bad. And for the unloading, you can just take the linear elastic, and then there will be some difference, but it's not so bad. So in summary, the influence of the loading speed is considered through the assumption of elastic perfect viscoplastic behavior of the joint, multi-layer bed joint. And of course, this model is developed and calibrated. So this C is calibrated through the results for with the multi-layer bed joint with rubber granulate core soft layer. It could be also, of course, extended if we get some other results for some other materials that could be used as core soft layers. So this is actually the end of the first presentation. And if you have some more time, I can just quickly show what we actually did in other projects, maybe 2 slides per project, something like that. So the first project that was also financed by Swiss National Science Foundation was deformation capacity of masonry. So we tried actually to close some knowledge gaps through this project, and we started with survey of and assessment of existing experimental and theoretical research in this area. Then we did a lot of tests also on big walls, on small walls, on small specimens, and so on. And then we suggested some refined empirical model to calculate displacement capacity of unreinforced masonry walls. And this is, of course, only valid for the walls that are done with Swiss materials, because that's what we tested. And we also developed some new constitutive model for unreinforced masonry under revolver, semi-cyclic compression, and some mechanical model for the force replacement response with the failure, flexure failure mode. What we didn't succeed again here is to develop a model for the shear failure. And in my knowledge, I think that is still an open problem. Also in this case, I don't want to go in details. What I want to pick up from this project are some interesting things that I called the beauty of nature laws. So what we find out is that the stiffness during this cycling loading decreases following approximately an exponential law, and eventually this stiffness falls to zero. So this exponential decay of the stiffness K0, that is the stiffness at the beginning of the test, that means that this stiffness decreases from its initial value at the rate proportional to its current value. So we can write the differential equation, we can integrate. A is here the exponential decay constant, and K0 in it, that is the initial value, which we can get from the results. When we put that in diagrams, we can see that that is actually very good prediction. And of course, that is just a numerical thing, but what is interesting here is that the similar processes decays occur in nature, for example, radioactive decay, and also in engineering sciences, for example, the vibrational decay in damped oscillators. So all these processes can be just described with this same differential equation. The second thing that we find out is, or not find out, that we just noticed and use. So this is a typical measurement mesh for a small specimen. So that are these triangles, and we are measuring their changes in distance between these net nodes. And in order to correct measurement errors, which is must there, the analogy between the principles of the minimum of the sum of squared errors and the minimum of elastic strain energy was used. And this is how it can be done. We can use the standard finite element software where the measurement net was modeled as statically indeterminate. If it is not statically indeterminate, it won't work. Plane truss, and the truss members length changes were applied as a loading. And in this way, the nodal displacement could be obtained. Of course, you have to put some supports, otherwise that won't work. So it's relative to these supports that we choose. The next thing that could be interesting is the reliability of structural masonry, and our group was doing that for a long period of time. So we firstly developed a probabilistic model framework for design of masonry. Then we used Bayesian assessment of the compressive strength for the masonry. We checked the probability and structurability assessment of mortar joint thicknesses in load-bearing masonry, and we also investigated the influence of workmanship on the compressive strength of structural masonry. The most two interesting things are these joint thickness. So if you on the left side, we have some distribution of the bed joint thickness in one wall. So the idea was there. So we visited several building sites that were near our university campus, and we measured the joints, vertical and horizontal joints. And this is the typical distribution in the wall of the bed joints. And you can see as the wall is going to be higher, that means the course is going from 0 to 12, these joints will be thicker, because the masons, they usually cannot really have each joint 10 millimeters. So at the end, they have to fit the height between the two slabs, and then the joints at the top are much thicker. So we then try to find out how that can impact failure probability. And on the right side, you can see the diagram. So if you have the bed joint thickness of 10 millimeters, then the failure probability would be, let's say, 0.2 times 10 minus 5. And if you have, for example, 20 millimeters, which is very easy to find. So in this case, on the left side, we have even 25. So you get 4 times higher failure probability. And it is enough that just one joint is thicker than the other ones. And of course, that is very important and very interesting. And the details can be found in this paper, which was published by myself and Professor Stewart from University of Newcastle, Australia, in structural safety, who is interested in details. So the other thing that we find out is what uncertainty can done, or how uncertainty can change the behavior of the masonry. So this is, I just titled it Uncertainty Rules. Rules meaning the first explanation from verb. So exercise ultimate power or authority. And that means following. So as a part of the course of this structural masonry, which I did in Zurich, we have, during one lecture that is 1.5 hours about, the students are divided in small groups, and they are going to build some typical specimens. And at the same time, we have two professional masons, which are instructing and helping students during the exercise, and they are also building one specimen. After 4 weeks, we test that, and these are the results of these tests for the actually 11 years, from 2007 to 2017, and these walls were mostly clay block masonry. And you can see in this diagram the values that are achieved by masons are great. So with the gray color, and others are the students' results. So depending on the year, we have at the beginning, there were not so many students, so we have a smaller number of specimens. And then in years 2015 and 16, we have really a lot of students, and then we have, of course, a lot of specimens. And what is here interesting is that the specimens that are built by students are sometimes actually get higher strength than that what masons are doing. So this is the comparison, the strength ratio, actually between the values of the walls which were built by masons, divided by actually the sample mean. So it is more or less between 0.9 and 1.1. That means so that the strength of wallets built by the masons was almost equal to the average value of those built by students. And in the course of these 11 years, professional masons could not overperform unskilled students. So one possible explanation for such outcome could be that the professional masons are more consistent in their work, and thus their values are always in the middle. On the other hand, from border point of view, question arises if the skill is so important. It seems that the only advantage of professional masons is their construction speed. Other advantages, such as high quality and low variability of workmanship, seem to be overcome by uncertainty. So this is very interesting thing. So I have only 3 slides left, telling something about hybrid testing. I suppose you know what hybrid testing is, and we did that also some let's say, two smaller projects in our lab and also theoretically. And what we find out is that there was a new substructuring method for planar masonry substructures developed, and this aims to just reducing the number of actuators which are necessary to achieve predetermined coupling accuracy between physical and numerical subdomains. So that was the purely theoretical work, and we also did some testing. We did a hybrid testing of single-story masonry wall with asymmetric door opening. Of course, we tested that several times on same test specimen, and it was subjected to 1979 Montenegro earthquake at different scales. So this is the isometric picture of this wall. So that's the same 3-actor setup that we use for other tests. This is the second last slide. So we developed this digital image correlation in-house system, and we use that, and we are really very satisfied. And in this paper that is given here, everything is explained in detail. And I always get the question, well, could we forget LVDTs, for example, and use only this one? And I think we are now at that level that we can just use this digital image correlation, actually. So thank you for your attention. And if you have any questions, we can I can try to answer them. Otherwise, you can write me email anytime. This is my email address given here. So I'm open for questions and discussions. Thank you.
Thank you, Nebojša. It was a very interesting and comprehensive presentation. So I would like to start the discussion now. And I kindly ask the audience to pose a question if someone has.
Yeah, this is from Zurich. Thank you, Nebojša. We're going to pack up because somebody else is coming to the classroom, but thank you very much.
Thank you.
Anyone from the audience, or shall I start, as always, this discussion part? So what I'm interested in is what is the current situation in the design codes regarding the topic? Can you put some light on the situation in some major codes, let's say, in the Europe, in the US, in Switzerland, of course?
So what I'm also active in, actually I'm chairman of the Swiss Code Committee, and we introduced some clauses that are actually connected to these layers. As I mentioned before, you can get some loss in the strength, vertical strength, if you put these layers about 10 to 15%. So it's not, let's say, if I may say so, bad, because we have the safety factor gamma m in Switzerland is 2.0. So it could be covered, but of course, the idea of gamma m is not to cover such things, but to cover some uncertainties. Anyway, and there are some different standards for these materials, but there is no actually, nobody's thinking in this way that we taught here, and that's of course is normal, because we found something, let's say, relatively new, and it takes time for these things to get in the standards, and it will be not so easy, especially now when also in Switzerland we were a long time independent of the Euro codes, but now we decided to take Euro codes as standard, and it should be, I think, in 2028 that will be the case. So we will, let's say, revoke all our codes, which is actually pity, because, for example, Masonry code, Swiss Masonry code has about, I think, 40 pages, and the EC6 maybe 200 or something like that. And the big advantage, the great advantage of Swiss codes is that in each code, also in masonry code, there is a clause telling if you can that better, or if you know better, you can do it, but you have to prove theoretically or experimentally that it is like that. And if you go to Eurocode, for example, in Germany, if you want to introduce something new, you have to get some papers from DIN and so on and so on. So it's not so easy. It's not open to market actually, and that's one thing that actually will be missed, I think, in Switzerland, that you won't be anymore so free to do that. And as I said, there is a lot of people using these layers in Switzerland, especially as a sound insulation, and actually nobody think about what does that mean to the strength of the masonry, to this displacement capacity, and so on and so on. And I hope these projects would bring some new light, shed some new light on that, let's say, not problems, but that issues. But it is not actually that there is no some code clauses that says if you do this, then this will be better for to get, it will be good to get a good deformation capacity of the walls and so on and so on. That's not, you cannot find that in the codes. If that was the question.
Yes. I was assuming that this is the situation, so this perhaps represents an opportunity to integrate some of these findings which you achieved and your colleagues to the codes. And I surely hope that we will, because the codes for the masonry structures worldwide, they're not outdated, but they rely on some old and, let's say, proven principles. But I kind of have a sense that, or a feeling that we're missing some, at least small step forward to improve, to modify ourselves, in this direction.
Actually, we did some step in this direction, because there was a revision of the Swiss Masonry Code a couple of years ago, and we introduced the deformation-based method for the masonry, and that is actually the only structural code in Switzerland that allows that. For example, in concrete code, you are not allowed to use deformation-based methods. Of course, they are very dangerous. So you have to know what you are doing, because, and I don't know, that is one way of doing something, but it could be really dangerous looking at today's students and their knowledge on structures, statics and dynamics and so on. Because the idea is, well, we have this was introduced from two different points. One point was to allow people to use something which is not really too conservative and so on and so on. And the other thing is that the industry was pushing that, because they say, well, if I have higher earthquake loading, which was introduced in Switzerland, I also have a very bad opinion on that things. If you, for example, if you take Basel, that is the city in Switzerland, it lies on the Rhine between France, Germany, and Switzerland. And for this point, every of these three countries have different rules how to design according to earthquake, and that's stupid, because that's one point. But okay, nothing could be actually ideal, but this is, I don't know. And the industry was pushing us to introduce this method, because they find out, of course, they are looking only money. They find out they don't need to do, for example, reinforcing, because if you use standard method, you say, well, this doesn't work, you have to reinforce it. Then you use a deformation-based method, and you can find out, yeah, still it works without reinforcement. But as I said, that could be dangerous, because the deformation method is always on the unsafe side.
Yeah, I know.
And the other one is always on the safe side, but people say it's conservative. And if you check the the overall safety factor, let's say, when you put all together for Mason in Switzerland is between 4 and 5. So it is too much. But I saw so many examples. The people are doing everything. They are cutting the chassis through the walls that should take horizontal forces. Yeah, they're making holes or whatever. So you have to have higher safety factors because people are not doing that correctly, actually. And that's the only way to save it.
And they're unpredictable. The behavior
of course.
of the people.
Well, for example, this story with chassis in Switzerland, when the building is finished, then you get electric guy and he's coming with a spray and drawing where you have to put the chassis. And then there are companies that are doing only that. So they come 2 or 3 people with the equipment and then just cut the chassis, then go away. So there is no engineer to check if it is okay to make chassis. They are making chassis through joints or unbelievable. What I have seen, it's really unbelievable. We had a case that I suggested that you have to take it down and build a new one. So this will take no loads. Unbelievable.
I can only imagine. Okay.
Yeah, because after that, you put the color on the wall and you see nothing.
Yeah, it's hidden.
Yeah, of course.
Okay, thank you for response. Do we have any more questions from the audience? Apparently no. Okay, so Nebojša, I believe that all of the participants are from Serbia, so I'm gonna switch to Serbia now.
Yeah, of course.
Hvala vam za sjajnu prezentaciju. Ja sam uživao, verujem da su i ostali. I onako, tema je vrlo interesantna i neke stvari su mi sada jasnije, a najintrigantnije je od svega zato što mislim da će ovo tek da dođe na dnevni red kod nas, a vi ste nam danas pružili neki rani uvid, ako mogu tako da se izrazim. Hvala na svemu, hvala publici i nadam se da se vidimo narednom prilikom uživo. To bi bilo lepše nego ova varijanta.
Okay. Važi, ja ću vam spremim ovaj PDF s tim što vjerojatno da neće se vidjeti ovaj film, ali to nije bitno, mislim.
Ne, to je u redu prezentacija.
Onako sad prezentacija oko 100 MB, to je suviše veliko, ali kad je PDF on će biti mnogo manje. Ja ću vam spremim, provjerit ću ove što smo rekli slike i tako dalje.
U redu.
Ok.
Hvala vam. Svako dobro i prijatno večer.
Ok, prijatno, čao.
Doviđenja.